Okay, moving along here with balancing some of these equations. The next equation here that we haven't covered yet, we start with a molecule here, C4H10, so 4 carbon atoms, 10 hydrogen atoms. Right, we're combining that with oxygen, right? So generally combining something with oxygen is called a combustion reaction. So this is a combustion reaction, and C4H10 is actually butane. The same thing you might have in like a disposable lighter is usually butane. So anyway, start at all the way at the left here, 4 carbons. So we're going to at least need 4 carbons over here on the right side. Now we do have to keep in mind, it might not work with just 4 carbons there. So we've got to be prepared and willing to change things up if things don't work. But that would get us to balance in terms of carbon. Next is hydrogen. There's 10 hydrogens here. There's only 2 over here on the product side in water. So I can get to 10 by putting a 5 in front of the hydrogen. So 5 times 2 is 10 hydrogens over here on the product side. So I'm good with carbon and hydrogen. Now I just need to look at oxygen. If I have 4 molecules of CO2 and there's 2 oxygens in each CO2, that would be 8 oxygens, 1 oxygen in each water, but there's 5 waters. 8 plus 5 is 13 oxygens. Now, 13 oxygens on the product side, but oxygen comes in units of 2 on the reactant side. So I cannot get to 13 by adding together quantities of 2 oxygens, right? They got an even number on the reactant side, an odd number on the product side. But just like we saw with 3 and 2 before in terms of ionic formula or in terms of balancing an equation, right, it's the least common multiple that is going to be important. So if I have sets of 2 over here, and when I added these together, I had 8 plus 5, or 13 oxygens. The place where I'll be able to balance those is the least common multiple of those 2 numbers. So the least common multiple of 2 and 13 is 26. That means I need enough oxygens on the reactant side to get to 26 total oxygens. So that would be 13 O2. And if I need to get to 26 over here, I need to double what I currently have, because doubling 13 would get me to 26. So if I have 8 carbon dioxides and 10 waters, 8 times 2 would be 16 oxygens from CO2, plus 10, because 1 from each water, would be 26. So now I have 26 oxygens on the reactant side, 26 on the product side, right? And I'm good in terms of oxygen. Now all I have to do is factor in the fact that I changed the numbers of carbons and hydrogens, but we did that in a fairly straightforward way. We doubled them. So if I have 8 carbons here now, to get to 8 back here on the reactant side, I would just need a 2 in front of the formula. 2 times 4 is 8. 10 hydrogens or 10 waters would be 20 hydrogens. And I now also have 20 hydrogens because of the 2 that I put in there. So in this case, the correct coefficients for this reaction would be 2 butane reacts with 13 oxygen, and that produces 8 carbon dioxide and 10 water molecules. Okay, so again, there's a back and forth there, but really we're counting, and we're using elementary school multiplication, 5 times 2, 13 times 2, that sort of thing. Now, if you're not as comfortable with multiplying, right, you can keep a little tally here, right? This is really applying counting to each side of the equation, so you want to do what you need to do to get it right. But I think in a lot of cases, people make this out to be much more complicated than it is. That you're really just counting atoms on each side and making sure that they match up. Okay, now the last one here on the first page, we start, here's ammonia again, just NH3 neutral, right? So keep in mind ammonia, ammonium, the polyatomic cation you should be a little bit familiar with by now, is a little bit different thing. So watch out in names when you're trying to name something with ammonium in it. Ammonia plus oxygen. And this is giving us NO, nitrogen oxide, nitrogen monoxide, and water again. So we want to approach this in a similar fashion. 1 nitrogen here, 1 here, that's fine. 3 hydrogens here, 2 over here. Okay, so we know that ratio at this point. We can try a 2 here and a 3 here. That would get us to 6 hydrogen over here, 6 hydrogen over here. That's good. Now we did change nitrogen. So if I have 2 nitrogen over here, the only other source of nitrogen on the product side is the NO. So I'll put a 2 there. Right? That gets nitrogen and hydrogen. Now I do have to worry about the oxygen. So 2 NOs, that would be 2 oxygen. 3 waters would be another 3. 5 oxygen on the product side. It again comes in sets at 2 here on the reactant side. So in this case, I've got 2 on this side, 5 on this side, but I can balance it if I go to the least common multiple of 2 and 5. So I need to get to 10 oxygens before things will be balanced. That means I need a 5 here in front of O2 to get to 10 total oxygen atoms on the reactant side. Right? And if I double each of those, 4 for NO, 6 for water, that would be 4 oxygens coming from the NO, 6 coming from the water, that would get me to 10 on the product side. So oxygen is balanced. Now I just need to factor in what I've done to change the nitrogen and the hydrogen. So 4 nitrogens, 12 hydrogens, right? But an easier way to keep track of that is we doubled both of those, meaning we need to double this. So 4 ammonia would be 4 nitrogens. That would balance with the 4 nitrogens here. 4 times 3 would be 12 hydrogens in the reactant side. 6 times 2, 12 on the product side. And there, that equation is balanced with 4, 5, 4, and 6 for the coefficients. Now, one thing to keep track of, if you're going through and you're balancing an equation and you end up with all even numbers, you don't have the simplest ratio of all the components. So in the back and forth, sometimes you might end up at a higher multiple than you need to be. So you go through an equation and you see that your coefficients are 4, 4, and 2, right? That would be a lot simpler if you divided through by 2 and just had 2, 2, and 1. So keep an eye on that, because that's not really correct if you have a higher multiple than you would need for the equation. It may still be balanced, but it's not presented as simply as it could be or should be in our reaction. Okay, a little more time. Let's move on to the next page here before I cut this one off. Okay, now we want to start to think about some of the things that we can calculate related to molecular formulas. So there's a couple definitions here that we'll go through, and then I think by the time we get to the calculations, we'll probably be on to the next video. But we want to start to think about atoms, molecules, and this new idea called moles, which is something that tends to frighten people, and people think it's a lot more complicated than it is. It's really just a counting tool that we're going to use. Okay, a couple things here that we're going to want to think about. The first one is called the formula weight. Now, formula weight is a term we will really only use through chapter 3, and not even to the end of chapter 3. The much more common term here is called the molar mass. They are equivalent, and they can be used interchangeably, but once we learn what a mole is, the term molar mass will be something we come back to much more frequently in the future. But formula weight, this basically is the weight that goes along with a chemical formula. So if we have a chemical formula, we can figure out how much it would weigh. This is quite simply the sum of the atomic weights of each atom in the chemical formula. We know where to find atomic weight, atomic mass in the periodic table. If we have a compound with multiple atoms, we add up the atoms. That would give us the formula weight for that molecule or compound. Okay? And we'll practice that a little bit lower. The other thing we want to think about here is the kind of the definition of what this concept of a mole is. So there's this idea called Avogadro's number. Some textbooks have started to call this the Avogadro Constant now. I'm not sure why we need to change the name, but just keep that in mind. If you see the Avogadro Constant, that's referring to the same thing. Avogadro's number, or the Avogadro Constant, is 6.022 times 10 to the 23rd power. What this represents is the number of particles in a unit of amount called the mole. Now, when we're talking about particles, generally we're either referring to atoms or molecules, and that would depend on what chemical formula we're looking at, right? But you could use this for anything. This is not a lot different from the idea of a dozen. We use a dozen to count things like eggs because it's easier to say 3 dozen eggs than it is to count up all 36 eggs. This is just a significantly bigger number. It's still a way for us to keep track of atoms because atoms are much smaller We need a lot of them to get to the point where we have some useful units. So I have it here as an equality. If I use the term mole here, 1 mole of carbon-12 would be 6.022 times 10 to the 23rd atoms of carbon-12, right? And like we saw before, any equality we can use in a calculation as a conversion factor, right? And that's where we'll maybe get a better handle on what this means when we start to look at using it in a calculation, which we'll start in the next video.